I'm going to finish up the notes for section 3.3, and maybe you've already started the homework, hopefully, but we are going to do number 43 together, and then I'll do a couple more things, and I should be able to get this in a 15-minute video if I talk kind of fast. You might need to tell Ms. Shiro to pause it sometimes if you need to catch up. But if you were to open your book to page 186 and look at number 43, you're given the function f of x equals x over 2 plus cosine x, and we're analyzing it on the open interval from 0 to 2 pi, and we are trying to find where on the open interval from 0 to 2 pi, and this one had multiple questions, we are supposed to find where the function's increasing, decreasing, apply the first derivative test to identify relative extrema, and confirm it on a graphing utility, which I'm not going to do, but you should do it. I don't know that I'll have time in the 15 minutes to get all that in. So first thing we need to do is we need to find the derivative of the function, because where the derivative is 0 is where it must have changed from positive to negative or vice versa. So taking the derivative of 0, it's a nice easy one, we'll set 0 equal to 1/2 minus sine x, meaning that we're looking for where the sine of x is equal to 1/2 on this open interval. So then when I go to my unit circle, remember sine of an angle is 1/2 at pi over 6. Sine is the y value, so it's root 3 over 2 comma 1/2, or that much up. So we're also looking over in this quadrant, which would be back pi over 6, which would put us at 5 pi over 6, which you guys know how to find those. So Ms. Shiro, they won't have a problem understanding that. So we will take, and we need to look, and I like to make a derivative graph. I like to open it at 0 and 2 pi. If we were going to the infinities, I wouldn't do that. I would just put those on the end. I'm analyzing the derivative of my function. I know that it's 0 at pi over 6. I know that it's 0 at 5 pi over 6. So I'm going to find where the function is increasing and decreasing by testing angles in each one of these regions. So if I was thinking of an angle between 0 and pi over 6, again, you don't really need to be exact. We just want to see if this would be positive or negative. So when I go to my unit circle here and I think of an angle over here, you can see that that y value is obviously going to be less than 1/2. So when I do 1/2 minus the sine or the y value of an angle less than or lower than it, it's still going to be positive. If I were to pick an angle between pi over 6 and 5 pi over 6, I'd probably choose pi over 2, and its sine is 1. So when I do 1/2 minus 1, I end up negative. And again, I did tell you for the sine and cosine waves, you can know in the back of your head that those are going to alternate from positive to negative at those zeros, but you should still be able to supply support and evidence of why if you had needed to. So I am right now knowing that my function is increasing, because that was one of the questions. It's increasing from 0 to pi over 6 non-inclusively, and it's also increasing from 5 pi over 6 to 2 pi non-inclusively. Likewise, it was decreasing in between them, so I'd say decreasing from pi over 6 to 5 pi over 6. The second part of the question, so that was part A. The second part of the question, part B, was to identify the relative extrema. So remember, the first derivative test says that if the function goes from increasing to decreasing, and what we have is a relative maximum of the function. So you would say a relative max occurs at, and we'd have pi over 6 comma, and it's really that y value we're concerned with. So I'm going to go through finding that y value for you for the first part, but for time purposes, I'm not going to show you where the relative min occurs, because we're also, since we're decreasing, increasing, we have a relative min at 5 pi over 6 comma, and I need to go find that. So I'm going to go show how we find the y value. So we go back to the original function, because that's the one that we're trying to find the extrema on. And on the original function, f of x, in this case I'm trying to decide what it is at pi over 6, because I know I have a max there. So f of pi over 6 is going to equal pi over 6 over 2 plus cosine pi over 6. believe that was the original one. Yeah, I forgot the x on that when I wrote it. So when I'm trying to find what I've got there, I've got pi over 12, and cosine pi over 6 is root 3 over 2. In order to add those, I need a common denominator, so I'm going to multiply top and bottom by 6. I get pi over 12 plus 6 root 3 over 12, which would give me pi plus 6 root 3 over 12. So if you look in the back of the book, it's going to say that there is a relative maximum at pi over 6, comma, and then right here it'll say pi plus 6 root 3 over 12. I'm not going to go plug the 5 pi over 6 in there for the relative minimum. So on the next part, I think I'm not going to, I'll go back to this if necessary, but I'd like to go on to right here. It says day 2, it's actually, it is day 2, I guess, of 3.3. I was thinking it was third day, but it's my third video. So it's very important to know what graph you're being shown, because in this class you will be given the graph of sometimes the original function f, sometimes f prime, and sometimes even f double prime, or the second derivative. So this is the original graph of f. And if I were to sketch the graph of the derivative, we did that last chapter. Key points to notice, though, is that when you're doing the derivative graph, you're doing the slopes of the tangent lines. And right here, the slope of the tangent line is 0. So that'll be an x-intercept on the f prime graph. That's important. So I would like you to write this down right here. The relative max and mins of f, the original function, are x-intercepts of f prime, and vice versa. So that's an x-intercept. This max right here has a tangent line with a slope of 0, and right here we have a tangent line with a slope of 0. So if I were even to make a derivative sine graph over here, and I were to say, well, where is the derivative equal to 0? You can see at about negative 1.5 at 0, and about 1.5, that's where the derivative is 0. Those provide me with my x-intercepts. Now, if you look at this region of the graph, from here to here, I've got negative slopes. What that means is my derivative graph is going to fall below the x-axis, or my y's will be negative. In between here, from here to here, they will be positive, and now I'm decreasing, so it'd be negative, and then increasing again, so it'd be positive. So now what I can do is, I can use all that to give me a good graph of the derivative. So again, when I'm drawing the derivative graph, I say, where is the slope of the tangent line 0? And it's at these maxes and mins, and then I analyze increasing and decreasing on the original function. So because this was decreasing on this side, my derivative is negative, so I come from the negative. And then in this region, I'm going to go above the x-axis. I will be its most positive where the tangent lines are most steep, about right in the middle here, which means it's going to peak out like that. Likewise, this whole part of the graph is downhill, which means my whole part of my derivative graph is going to be negative, or below the x-axis. It's the most steep right about there, so it's going to bottom out. So you can see kind of how that derivative graph can be read forwards and backwards. And now, in Chapter 2, you only read them forwards. It would give you the graph of f and have you draw the graph of f prime. Well, now what we're going to do is draw a double bar there, because these are completely separate problems. So draw a double bar so you know that I'm starting a new train of thought here. So now it says use the graph of f prime. What they're telling you is this is the graph of the derivative of the function. And it says identify the intervals on which f is increasing or decreasing. So they're giving me the derivative and asking me questions about the original function. Well, let's take a look and see if we can figure this out. F is increasing. Just ignore the graph for a second and make sure you understand the question. F is increasing when the derivative, the tangent lines, are positive, when it's going uphill. So we need to go to our derivative graph and say, well, where is the derivative greater than 0? And that would be where the derivative is above the x-axis, right here and right here. The f prime, remember this is graphing the point x comma f prime of x. and that y value is positive when it's above the x-axis. So you have to look above the x-axis when we're trying to find where the derivative was positive. So in this case, that would be from negative infinity to negative 3, union 1 to infinity. All right? Likewise, f is decreasing when the derivative is less than 0. So we're looking on the derivative graph where it falls below the x-axis. That would mean my original function's derivative was negative. Yes, I know it was the most negative down here, but in this whole bottom part of this bowl right here, I am graphing the derivative, and it is negative down there. So that would be from negative 3 to 1. And then it says to determine max and mins. Well, remember, max and mins are where the function goes from increasing to decreasing, or where the derivative goes from positive to negative, or vice versa. So these x-intercepts are indicating the maximum and minimums that we had. But again, back to this graph. When we had the original, every minimum gave me an x-intercept, and likewise with the relative maximums. So what I know right here is, yes, the derivative was 0, which means the original function either had a peak or a valley. But in particular, right here, because it went from positive to negative, I would say at x is equal to negative 3, we must have had a relative maximum. Because the derivative was positive, then it went negative. At x equaling 1, we must have had a relative min. Because you can see a relative min because you can see that the derivative was negative in this whole region, which means the function was going down, and then it changed to positive. If I were to draw the original function from this graph, it would be a cubic, and it would have a relative max right here. Go like this, probably. It would be positive, positive, positive slopes, 0 right there. This whole region would be negative all the way down here, right? It would be its most steep downhill right in the middle, and then it'd probably go like that. That would have been the original. All right, so moving right along here, what do I have up next on my next page? It looks like I've got just a little bit of time, so I just want to look at number 89 on page 189. If Miss Cheryl could pause the video, I'm going to try to get as much of it in as I can. Let you get your books open, but this is one where we're going back to the position. We actually answered these questions pretty thoroughly in chapter 2, so it should be a good review for you. And you are to find the velocity function, first of all. So remember, velocity is the derivative of position, so you should be very comfortable saying that's 6 minus 2t. That's part A. Then it says identify the time in which the particle is moving in a positive direction. So I want to know, when is the velocity greater than 0? So I made what I would call my derivative sign chart. In this case, my derivative is velocity. I know that it's 0 when 6 minus 2t is equal to 0. So at 3 seconds, I know that it's 0. And this says I'm analyzing this starting at time 0. It says for all times greater than or equal to 0, and I'm heading out to infinity. And the question is, when is the particle moving in the positive direction? So I've got to test my intervals to see where the derivative is positive. If I pick a point in here, say 1, that would be positive. If I pick a point to the right of 3, like say 4, that derivative is going to go negative. So what it means is the particle was moving forward for the first 3 seconds and then backwards the whole rest of the time. And there was only one point at which it changed directions, and that was when its velocity was 0, or at 3 seconds. So part C says identify the time intervals in which the particle is moving in a negative direction. So for part B, we'd say from 0 to 3, and that you can leave that open or closed, is when it's moving in the positive direction. And for part C, we'd say from 3 to infinity is when it's moving in the negative direction. And now it says identify the time at which the particle changes direction. Well, it changes direction when t is equal to 3. That's where the function went from increasing to decreasing. So we are done. You can continue your work with 3.3 and that'll be due tomorrow. If you have any questions, you can always post them on Edmodo. I'll be checking that regularly. See you guys.